Hello there, Gregory Carlson here for College Algebra, Section 3.5, Part 1. And we've analyzed parabolas, we've analyzed cubic functions, so now it's time to analyze hyperbolas. So here's what the generic graph of a hyperbola looks like. It's equal to y equals 1 over x. And it's interesting because putting x in the denominator really messes with the graph. You know what the graph y equals x looks like, where it's just a line? Pretty boring. But y equals 1 over x makes really strange things happen. You get all sorts of curves. So let me show you. First, if it's just plain y equals 1 over x, there's a vertical asymptote at x equals 0. We see that we can't plug in a 0 for x because that would be undefined. So we have an asymptote at x equals 0. And it's a vertical asymptote, so it's x equals 0 because that's a vertical line. There's also a horizontal asymptote, so that's the vertical asymptote. There's also a horizontal asymptote, and it's horizontal, so that means it's y equals, and it's y equals 0. So let's talk a minute about why that's an asymptote. Can y ever equal 0? Look at this. Is there any number we can plug in for x that would make y equal 0? You could plug in 100, and that'd be 1 over 100. That's a pretty small number. Or you could plug in a trillion, and 1 over a trillion is a pretty small number. But no, there's no number that we can plug in for x. You can't plug in 0 because that's undefined. You can plug in any negative number you want, and as x gets bigger and bigger, y gets smaller and smaller and smaller, but y can never be 0 in this formula. So let's plug in a point. If you plug in 1, you see that 1 divided by 1 is 1 is going to work, so we get 1, 1 as a point. If you plug in 2 here, you plug in 2 and a half, so you get a half right there. Then it's going to be a third at 3 and a fourth, and so on. So it's going to get closer and closer and closer to this horizontal asymptote, but never touch it. So that graph is never touching. And over here, if we plug in fractions, that's going to get flipped and make it bigger. Like if you plug in a half right here, that's going to become 2, because 1 divided by a half is 2. So it gets bigger and bigger and bigger up to this asymptote as well. Now, you could plug in negative numbers as well, and if you do that, you're basically going to get the reversative. There's the point negative 1, negative 1, and it's basically the mirror image, which actually makes this an odd function. So that's how you graph the hyperbola y equals 1 over x. It's a pretty exciting graph. It's not continuous all the way through because it's discontinuous right here. There's a step discontinuity. What would the graph of y equals negative 1 over x look like? Well, it's basically, as you know, when you put a negative in front of a graph, it just flips that graph. So our asymptotes stay the same. Just like that, the asymptotes are the same, but essentially instead of being in the first and third quadrant, now it's going to be in the second and in the fourth quadrant. Just like that. So there you go. You're in the second and the fourth quadrants for the graph y equals negative 1 over x. Also, again, notice that the asymptotes will be x equals 0 and the horizontal asymptote will be y equals 0. How about this next one? So we're going to, down in this third graph the function y equals 1 over x minus 3. So you should notice that it's kind of been shifted, and the shift has happened with the x, okay? And so that means that it's going to be moving 3 to the positive direction because it's the opposite direction of this sign. So another way to think about it is, what would the vertical asymptote be? What value can x not be so that the denominator wouldn't be 0? And so you just solve the equation x minus 3 equals 0, but more than likely you could do that in your head. If you plugged in a 3 for x, you'd get 3 minus 3, which is 0. So the asymptote, the vertical asymptote, is going to be x is equal to 3. So our vertical asymptote is x equals 3. What about the horizontal asymptote? It's actually just the same as this. The horizontal asymptote, this fraction right here, because there's no x in the top, this fraction will never be 0. You can make x as big or as small as you want. We know x can't be 3, but y is never going to equal 0, so that's the asymptote. So over here on our graph, the asymptote, once again, is y is 0. That asymptote's not always going to be 0, though, so we'll look at an example in a minute of when this is different. So let's go ahead and graph it. The graph is basically going to be exactly the same as this graph. It's just been shifted over 3. So you can plug in some points if you like, but it's basically going to be this number here and this number here. So let's draw that in. And draw this one in. And this is because it's positive. Okay, what's the domain of the function? Well, there's a fraction, so there will be a restriction. The domain of this function is going to be everything, every input, every x, except 3. So the domain is going to be everything up to 3, and we cut out 3, and then everything after 3. That's the domain. What about the range? What values of y are there? We have every single value of y except for y equals 0. So the range, remember, looking at y, is going to be everything to 0, but then we're going to cut out 0. So everything up to 0 and everything after 0 is the range. Here's an interesting question. When is the function increasing? Look at this function really carefully and tell me where it's increasing. Let's see. We're decreasing, 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 decreasing. Decreasing, 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 decreasing. We're actually decreasing across the entire function. This discontinuity right here allowed for the function to always be decreasing. So it's actually never increasing. That's kind of strange. By the way, this graph, the negative version, was always increasing, as you can see. So where is the function decreasing? It's decreasing everywhere except 0. I'm sorry, it's decreasing everywhere except 3. That's what I meant to say. Because 3 is where we had this bizarre discontinuity. We actually don't have graph right here. It's not in the domain. So we're decreasing everywhere except for the discontinuity. And since we're talking about when, that's going to be an x value. All right, I've run out of graphs, and so I'll make sure that in your notes you have 4 graphs. But let's really quickly draw this next graph, this next one. So I can tell that my x-intercept is going to be, my x-asymptote is going to be x equals -4. What about the y-asymptote? So here's the x-asymptote. Now, we know this is kind of tricky, so bear me out here. Would you agree with me that this fraction is never going to be 0? Like with this one, we know that this fraction was never going to be 0 right here. So this fraction is never going to be 0. What does that mean about y? If this can never be 0, what can y never be? Y can never be 2. Make sure you really think about that. If this fraction right here can never equal 0, then that means that y can never equal 2. We could think of something to plug in for x such that this thing equals -2, and then -2 plus 2 would be 0. But because this fraction will never be 0, y will always be a little bit off of 2. So there's an example of a horizontal asymptote different than 0. And at the start of the next part, I'll show you a generic way to find the vertical and horizontal asymptotes. But I hope that makes sense, that y can never be 2, so that's the horizontal asymptote. So here is my graph. By the way, notice that we're all positive in here. So if there was a negative in front of this, then it would be flipped. But since it's not, we can just draw the generic graph. So I'll make sure you have a fourth graph on your paper so you can graph that fourth one as well. So those were vertical asymptote of -4, horizontal asymptote of 2. So that's how you graph simple hyperbolas. We'll look at some more complex ones in part 2.